Hello, chemists. This is Ms. Placino, and you're watching Lesson 11.3, An Introduction to Equilibrium. Today we're going to talk about what an equilibrium system looks like. We are going to kind of transition out of kinetics, where we're studying the rates of chemical reaction. We're going to try to apply that concept to these reversible equilibrium systems. Goals for today's lesson. You should be able to explain what equilibrium is and the characteristics of a system at equilibrium. And you should also be able to apply this concept to specific systems. We're going to be looking at phase, solution, and chemical equilibrium. So both of these are very important for today. Let's get started. When we're talking about equilibrium, we're referring to a state where two opposing processes are occurring at equal rates. So we basically need two things that are opposite of one another occurring at exactly the same speed. Let's look at an example that has nothing to do with chemistry. We've got this guy here. He has found himself in quite the predicament. What are the two opposing processes in this case? Hopefully we're thinking, okay, it's this bailing water out of the boat with that pail, and water coming into the boat, presumably from a hole at the bottom of the boat. How do you know they're occurring at equal rates? Well, if you look at the overall water level in the boat, it's not really changing. I guess we're rocking a little since he's putting in some effort to get the water out of the boat, but the total amount of water in the boat is remaining relatively constant. If I wanted to try to represent this process with an equation, I might do something like this. Water coming into the boat is in a reversible reaction with water going out of the boat. In order for a system to establish equilibrium, the process has to be reversible. It has to be occurring in a closed system, and it's got to be given ample time to equilibrate. So far, we've just been studying one-direction reactions, where the reactants turn into products. Largely, these processes that we looked at so far are not particularly reversible. Think about burning a piece of paper, for example. Really unlikely that you're going to be able to get the carbon dioxide, water vapor, and ash that you created and turn that back into paper. When we say occurring in a closed system, we mean we need a system where nothing is really going in or out. And finally, we just have to give reversible systems a little bit of time to reach this state of equilibrium. Anytime we go to write a reversible reaction, we're going to use this arrow. Kind of like a, split double-headed arrow. This represents that the reaction is reversible. Please note this does not mean the system is necessarily at equilibrium. It's just telling you that this process is reversible. In other words, you've got two different reactions occurring at the same time. We have our forward reaction, A turning into B, and we have our reverse reaction, B turning into A. So just kind of by convention, we'll still call everything to the left of the reaction arrow, the reactant side, to the right of the reaction arrow, the product side. This is going to be our forward reaction from left to right. This will be our reverse reaction from right to left. It's kind of the conventions that are used. All right, so let's put this concept into practice, and we'll start with a couple of systems that we've already looked at before. All right, you've definitely seen this picture before. This is an example of phase equilibrium, and we talked about this in Unit 7 when we were looking at vapor pressure. So we've got a liquid, we've got some vapor, we've put a stopper in our Erlenmeyer flask to seal the system so nothing can get in or out. And if we just wait long enough, we'll end up with equilibrium being established. In our example, what two things or what two phases are at equilibrium with one another? Yeah, we've got the liquid phase and the vapor phase. We know that if you've got something like water, let's say, and you've got it in a container and you cap it, over time, some of the liquid molecules are going to evaporate and become a vapor, and some of those vapor molecules will condense and reform the liquid. So, at equilibrium, the rate of vaporization, or the process of going from liquid to gas, is equal to the rate of condensation, gas returning to liquid. Now, to the naked eye, it doesn't look like anything's happening. We're too big to see the individual water molecules and the changes that they're going through, so it looks like there's really nothing going on inside that Erlenmeyer flask. But if you were able to shrink yourself down and see the individual water molecules, you'd be able to see that like this forward and reverse reaction are still taking place. We're still having vaporization and condensation occur. They're just happening at the same rate. So the total number of molecules in each phase does not change. If I wanted to try to represent this with an equation, you could write something like this. Liquid water is in reversible reaction with water vapor. It doesn't matter what side I put the liquid and the gas on. Remember, they're both products and they're both reactants. Let's look at another example. All right, up next we've got solution equilibrium, which we talked about very, very briefly in the previous unit. Let's start with what type of solution is existing in our test tube here. Let's say I got a whole bunch of solute at the bottom, the solution itself. High likelihood this is a saturated solution. Basically, the solvent is holding as much of the solute as it possibly can. You kind of have like a zoomed in view of what's going on, like right at that interface between the solute and the solution. What are our two opposing processes here? Hopefully you're thinking that the rate of dissolving, the rate at which the solute is, in this case we've got calcium fluoride, dissociating to form aqueous ions, so they're free floating in solution, is equal to the rate of crystallization, or the rate of those calcium and fluoride ions kind of rejoining to form more of the undissolved solute. Again, if we were just to look at this from like our perspective with the naked eye, it looks like nothing is happening. No changes are taking place. But again, if you could shrink yourself down and make yourself super tiny so that you can see what's going on at that interface between the solute and the solution, we'd still see that crystallization and the dissolving process are occurring. They're just happening at the same rate, so we don't see any overall net change. I can write solutions that are saturated with this reversible reaction arrow. In this case, I've got calcium fluoride as a solid and a reversible system with calcium and fluoride ions. And everything on the product side is aqueous. The last thing that we're going to talk about today are chemical equilibrium systems. And this is really what we're going to be focusing on moving forward for the remainder of the lesson. Any sort of chemical equilibrium system has to be with a reversible reaction. And we can't see this with one direction, forward reaction only. The rate of the forward reaction is equal to the rate of the reverse reaction. We can't be super specific with kind of the nature of the forward and reverse reactions the way we were with phase equilibrium, where you see evaporation is equal to the rate of condensation, or solution equilibrium, where the rate of dissolving is equal to the rate of crystallization. So we're just going to be really, really general here. The rate of the forward is equal to the rate of the reverse reaction. For this particular reversible system, we have N2O4, dinitrogen tetroxide, in a reversible reaction with two NO2s, two nitrogen dioxide. Just like with our other systems, if you were just to look at kind of a reaction vessel containing this reversible system, it would look like nothing was really taking place. Things are going to look very static. But if you could shrink yourself down small enough to see the individual atoms and molecules, we'd see that we're having this decomposition reaction and then the synthesis reaction still occurring, but just the total number of N2O4 and NO2 molecules are not going to be undergoing a net change. Big takeaways for equilibrium is that once equilibrium has been established, once a system is at equilibrium, the rates of the forward and reverse reactions are equal. So rates are equal at equilibrium. To kind of represent this with a graph, you've got your forward reaction rate, your reverse reaction rate, and once they are equal to one another, equilibrium has been established. You can also think about equilibrium in terms of the concentration of your reactants and products. At equilibrium, concentrations are constant. A really common mistake that I see is people think that concentrations are equal. No, they do not have to be equal. They just have to be constant. They can't be changing. It's possible to have more products or more reactants at equilibrium, but they cannot change in relation to one another. So if you're going to try to represent that graphically, you might get something like this, where the green line is representing the original reactants, the orange line is representing the products. You can see that they are definitely not equal to one another, but equilibrium has been established, and we can tell because the concentration of the products and the reactants are no longer changing. They are remaining constant. So those are the big takeaways from today's lesson. We're going to be building on these concepts as we continue to move forward through this unit. All right, that wraps it up for today. Thank you for tuning in, and I hope you found this lesson helpful.